Welcome back, everyone. We are doing the Doppler effect today. And if you remember the Doppler effect, it's where you have some kind of a sound source that's generating, but the sound source is moving. And as this is moving, then you're going to get crowding here. And these are very short wavelengths, and these are very long wavelengths. And short wavelengths will give you the impression that the frequency is higher. And the stretched wavelengths will give you the impression that the frequency is lower. So an approaching sound is going to appear to get higher in pitch as it comes to you. And then as it goes away from you, it's going to go lower in pitch. So there is a formula for this, believe it or not. You're going to have the frequency that you hear, which is going to change. So it's going to get higher and lower. This is the perceived frequency. And it's going to be the actual frequency, whatever the engine is doing. So what, like the motor on the motorcycle or whatever, that is the frequency of the engine. But then we have to change it just a little bit based upon the observer or the listener interacting with that sound. Okay, so we're going to have the speed of sound. Okay, so the speed of sound, we're just going to call it nu. Plus, we're going to have a different speed, and that's the speed of the observer. So the speed of the observer is positive if it's getting closer to the object. So if, say, the object is stationary, but I'm moving towards it, it's going to appear to go higher in sound. Okay. Also, we're going to have that divided by, again, the speed of sound minus the velocity of the source. So for instance, if a motorcycle is the source and it's getting closer to me, then this is going to be a positive number. If it's getting moving away from me, that's going to be a negative number. Okay, so this will affect the frequency. Okay, so we've got a couple examples. First example says, Dad is driving the family station wagon to Grandma's house when he gets tired and pulls over at the roadside to take a nap. Junior is sitting in the back seat, watches the trucks go by on the highway, and notices that they make different sounds when they're coming towards him than they do when they're moving away from him. Number A, if a truck with a frequency of 85 hertz, okay, so that's its original frequency, 85 hertz, is traveling towards Junior with a certain speed, what frequency does Junior hear the truck approaching? Okay, so we have to fill in. So the first one is going to be the speed of sound. So we're going to first of all have that the sound is making 85 hertz. Okay, 85 hertz times, right? So we're going to have the 340 because that's speed of sound, meters per second. Okay, and then we're going to do his speed. Now he's not moving, right? He's at rest, so he's not moving, so we're just going to call that 0, of course. And then we're going to have the speed of sound again, 340. And then we're going to subtract, the sound that's coming at him, okay? But we need to know, is this V sub S going to be positive or negative? So remember that V sub S is positive if it's moving towards the observer, and it's negative if it's moving away. Okay? So it says, what frequencies does he hear as the truck approaches? Okay? So if it approaches, that'll be a positive, so it'll be minus a positive, so that's 27 meters per second. Okay, so calculator. 340 plus 0 divided by 340 minus 27 times 85 gives me a total of 92.3 hertz. Okay, so it has an original 85, but it has a apparent 92.3. It's approaching, it gets higher and higher in pitch and makes it sound like it's getting faster or higher. Okay. After the truck passes, what frequency does Junior hear as it's moving away? Well, the only thing that's going to be different is this is going to be a negative 27, so you're going to subtract a negative 27, which adds, so you're doing it again. F equals 85, 340 plus 0, because he's not moving, and then 340 is the speed of sound again, minus a minus 27, which is going to affect the 85. It's going to go lower than the 85 now. And you end up with 78.7 hertz. Okay? See, this is easy breezy. One way to tell if a mosquito is about to sting is to listen to the Doppler shift as the mosquito is flying. The buzzing sound on the mosquito's wing is emitted at a frequency of 1050 hertz. Okay, so that's its normal, that's its F sub 0. If you hear a frequency of 1034 hertz, does this mean the mosquito is coming in for a landing or that it has just bitten you and is flying away? Fantastic question. Okay, so you compare these two. Is 1034 bigger or smaller than 1050? Okay, it is smaller. So since it's smaller, since the frequency is smaller, it must be, what do you think? Flying away. Because it's going away, because it's dropping the pitch. Okay. B says, at what velocity is the mosquito flying? Now here is a little bit harder. If you remember, you've got let me rewrite the frequency problem. Okay. F equals F sub 0, which is your original, okay, times the speed of sound plus the velocity of the observer over the speed of sound minus the velocity of the source. Okay, so I'm going to have to redo this whole kind of thing. So if I'm solving for V sub S, which is the source, how fast is he flying away? You're just going to reconfigure it. Okay, so you've got, all I'm doing is just kind of reversing that. I think that's right. Okay, all I did was solve for V sub S. Okay, and now I need to fill it in. Okay, so the mosquito has an original frequency of 1050. Okay, so the speed of sound is 340 minus, and then this is 1050, okay, times the speed of sound again is 340. You're not moving, so your would be 0, and then your perceived sound is that lower frequency, 1034. Okay, so what is that? Okay. You get a negative number. I guess that means it's flying away. It's flying away from you, yeah, so I guess negative because it's going left. So you have 526 meters per second. Okay, are you all educated? Hope so.